Why do we need slow cells? Now, like we looked at setup, there is something called as hold. See, for example, this is my clock. Here, A is launching, flop A is launching, and I want the flop B to capture here. I don't want FFB to capture here itself. Whatever A is launching here, it should be captured by B in this cycle. B should not capture the data launched by A in this cycle in the same cycle itself, because in this cycle B is supposed to capture what A launched in the previous cycle, correct? If suppose B catches what A is launching in this cycle here itself, it will be missing what A launched in the previous cycle, correct? That we don't want. That will be a problem for us. We will be missing some data, correct? We don't want that to happen. That means we need to guarantee a minimum delay. That is, the delay from here to here should be greater than the hold time. So the hold time of the flop is a time after the edge of the clock. I don't want the data to change. So the fastest change that can happen at the input of B should be after this window, so that I can reliably capture the previous fellow who came here. Clear? So to ensure that there are no hold issues at flop B, we need cells to work slowly. We don't want ultra fast cells. If I start working too fast, I may be violating the hold, because what my A is trying to give out may appear at B here itself. If the change at B is seen here, then I will have a hold violation. So I want this circuit to work fast, but it should not be too fast also. It should be optimally fast. That means we need some cells to work slowly also. This becomes a contradictory requirement. I want the cells to be fast to meet my setup. I want the cells to be slow to meet my hold. Hence, we need a variety of cells to meet these requirements. And this correct collection is what is present in the dot lib. Clear? Now, let us compare these faster cells and the slower cells. Okay, if I look at the faster cell and the slower cells, what happens in a digital logic circuit? If I look, the load in the digital logic circuit is actually a capacitor. Now, faster the charging and discharging of the capacitor, lesser is the cell delay. Correct? I'm able to charge a capacitance very fast. My propagation delay is very less, because if I look at a digital logic circuit, let's say I have a digital logic. What is the propagation delay here? The time for the input to be felt at the output. Now the input should rise. So from here to here, what is the propagation delay? The time for the input to cause a change in the input to cause a change in the output. Now, how fast will the input change? How fast will the input change? Will depend upon how fast he is able to drive the input. Correct? So if the capacitance here is large, this gate will be driving the other gate slowly. If the capacitance is small, this gate A will be driving B very fast. Okay, so if I want to charge or discharge the capacitance fast, we need more current sourcing capability, and more current sourcing capability means it is wide transistors. Correct? Because the current carrying capability of a transistor is a function of its width. So wider the transistor, lower will be the delay, but the price I'm going to pay for it is more area, because wide transistor occupies more area and it's going to consume more power as well. Because it's going to draw more current, it's going to consume more power. Narrow transistors will have more delay, but the advantage I get is I get less area and less power. So faster cells doesn't come free, they come with the penalty of area and power. This is a very important point we need to keep in mind, because we cannot get attached to the speed and we cannot compromise the area and the power. So let's look at the selection of cells. So we need to guide the synthesizer to select the flavor of cells that is optimum for the implementation of logic circuit. More use of faster cells, it's going to be bad in terms of area and power, and it may result potentially in hold violations also. More use of slower cells will be sluggish circuit, may not meet the performance. So we need to offer the guidance to the synthesizer to pick the correct set of cells, and this is what we call as constraints. So let us look at an illustration of synthesis, how it is going to happen. So here I have a code. So the first step the synthesizer is going to do is to do a syntactical check, and then it will start mapping my design. So this is my module. It maps to the top level ports of my design. Then I have a statement assign int is equal to A or B depending upon the selection. So it becomes a mux. Then I have a flop where the output of the mux is connected to the flop. So this code becomes a flop and the output of the mux is connected to the input of the flop, and the clock and the reset connections are made. And this is what is the conversion of the RTL in terms of the standard cell gates available in the .lib, and this is given out as a netlist. Thank you.